Let me talk you through this problem here. We're going to use these equations, right? So the relationship between gravitational field, force, and mass, right? So the force of gravity is, of course, mg, right? Okay, and then the relationship between electric field and force and charge, right? So therefore the electric force is equal to EQ, right? Okay, and what they're talking about in this thing is this ubiquitous problem in physics. Basically, you've got these parallel plates like this, and we've got these attached to some voltage source, right? And there's a negative charge in there. Okay, and the negative charge is suspended. And the way we do this, of course, is that we have an electrical force that's up. And of course, gravity is down, right? So basically, at the root of this whole thing, we're going to say that the EQ that's acting up, the electrical force, is equal to the gravity force, which is mg, right? Okay, so that's really the basis of this as we go. Electrical force up is equal to mg. Now let's answer this question here, right? That's a negative charge. And it says, which plate is positive? Well, to exert an upward force on this negative charge, you put the positives above it, right? Because it would be attracted to it. Negative is attracted to positive, and so that would generate an upward force. We don't want the electric force in the same direction as gravity, otherwise it just goes down, right? Okay, and we know some of these things, right? The mass is 0.310 times 10 to the minus third kilograms. That's kind of a funny way to say the mass, but there it is, right? The gravity, we're on Earth, so it's 9.81 newtons per kilogram, right? And the charge is negative 1.80 times 10 to the minus sixth, right? So E minus 6. That's the charge, right? And then the electric field, we can solve for that. So let's solve for the electric field just for kicks, right? So turn on the calculator, 0.31 E minus 3 times 9.81 divided by 1.80 E to the minus 6. Notice I'm ignoring the minus sign because I'm not smart enough to do anything with it. And I get that the electric field is 1689.5, and that's newtons per coulomb, or by the way, it's volts per meter, are the same units, right? Okay, so we now, okay, so this, the final equation that we're going to use here is this one. Okay, so there's this equation, there's this guy, right? And then the final one is that there's a relationship between voltage, electric field, and distance, right? Electric field is equal to negative the change in voltage electrical potential, right, over the distance, right? And so the 150 goes in here, right? And then the separation, which is actually what we're solving for, is there, right? So what we're going to do here is we know the electric field is this, so we'll just use that equation there. So I'm going to say that 1689.5 is equal to some voltage that we don't know. Notice I'm ignoring the minus sign because, again, I mean, it all works out, but I know which way the electric field is and all that stuff. Okay. Oh, wait. The V is, sorry, this V is 150. 150 over R. Right? Ignore this. That's not really there. Okay, so let's see. How does this work? I think I do this divided by this, right? 150 divided by the answer I just got. And I get that R is 0.08878 meters, which is 8.88 centimeters, right? All right. Hope that helps.